In my previous video about VLAN hopping, I talked about the first part, switch spoofing. In this video, let's continue to discuss double tagging. This is my lab environment. In the UniFi network controller for network setting, you can see I have a super secure VLAN, VLAN 88, and then a regular VLAN 66. Then in the left side of the diagram, you can see I use two UniFi switches in this video, Pro 24 and Pro Max 24. I connect two Linux virtual machines to the two switches. The victim computer is connected to this switch part, and in the right side, let me show you the switch part setting. So for this part 23, you can see the native VLAN is VLAN 88. It's super secured, and then for tagged VLAN management is blocked off. So basically this part is a access part for VLAN 88 only. There's nothing wrong about it, right? Then for this attacker machine, let me show you the Pro Max 24 switch. For the port 24, you can see it's set up in a similar way. So the native VLAN is VLAN 66 and the tagged VLAN is block off. So this switch port is also a access part and is for VLAN 66 only. Again, nothing's wrong about it, right? So if you watched my previous video, you can see by setting it as a access part, you prevent the possibility for the VLAN hopping simply due to you have a trunk part, right? So you already avoid that possibility. But in this video, you can see there's another security risk because even you set it this way, it may still end up with double tagging. Another two parts I want to show you are the two trunk parts because these are two UniFi switches, right? So I need to connect them using one part from each switch. For example, this part 26, because it needs to be a trunk part, of course, tagged VLAN management is allow all, right? And then for native VLAN, I set it to regular VLAN, which is VLAN 66. Again, on the surface, nothing's wrong. I already show you all the three parts settings. Simply from each part perspective, nothing's wrong. But let's see what's the potential issue. By the way, I'm also going to run 3 Wireshocks. For 2 of them, they will be running against physical parts, which were already set up as part mirroring to the victim part and attacker part. I'm running the 3rd Wireshark within the victim machine just to understand from the victim machine perspective what's the network traffic look like. Okay, having talked about the environment, let's get the attacking started. From the lower part, the two Linux sessions, let me check their IP addresses first. Okay, at this moment, if I try to ping the victim machine from the attacker, okay, it's not pingable. Why? Because as I mentioned, the victim machine is in VLAN 88, which is super secured. If I show you the security setting for firewall rule, you can see I have a firewall rule defined already. It will simply drop all the traffic from VLAN 66 to VLAN 88. So that's why even though now I'm pinging the victim machine from attacker machine, the packet won't be able to even reach the victim machine. It will be dropped by the router, by the gateway, right? Again, seemingly, I have a very secured, very protected victim machine in the super secure VLAN. Now, let's try to see whether we can work around the security setting. Check the diagram. The victim machine is in VLAN 88. So, in the end, I need to make sure whatever packet sent by the attacker, it need to reach the victim machine in VLAN 88. But the attacker machine, the native VLAN is VLAN 66 and is a access part. It will drop all other tagged VLANs, including VLAN 88. So it seems there's no way for this attacker machine even send out a VLAN 88 packet and reach the victim machine, right? So the idea to work around the restrictions is, okay, because the victim machine only accept VLAN 88, let me prepare a VLAN 88 packet, right? And then because the attacker machine can only send out packet for VLAN 66, okay, let's wrap the real packet using VLAN tag 66 so that we can make the switch accept this packet and forward it, right? This type of VLAN tagging is called double tagging, and you may be surprised it's a legit technique and it is mentioned in the VLAN standard. So there's no reason the switch doesn't support it. There are legitimate use cases for double tagging, but at the same time, it may be utilized to attack your network. As we can see for the attacker machine, the existing interface ENS18 supports the untagged packet for VLAN 66. But look at the VLAN frame we try to construct. The outer tag should be VLAN 66. So we need to have a new interface which has VLAN tag 66. I run command IP link to add a new link based on the existing ENS18. Give it a name, ENS18.66. This is the naming convention for VLAN interface. .66 meaning it's for VLAN 66. And then the type is VLAN. The VLAN ID is 66. In this way, I create a new VLAN interface for tagged VLAN 66. Then I assign a static IP address to the new interface. The IP address is in VLAN 66. Okay, now I have a interface which supports the VLAN tag 66, right? Based on that, I create another new one which is for VLAN 88. So in this way, I can construct double tags within the same VLAN frame. I run command IP link, add a new link based on the interface I just created, ENS18.66. Give it a name. This is a strange name already, right? ENS18.66.88, which means it's for VLAN 88 based on this interface. The type is VLAN. The VLAN ID is 88. Okay, similarly, I need to assign a static IP address to the new interface. Okay, I give it .88.88 IP address. So now I have two new interfaces, but I cannot use them yet because I haven't brought them up yet. So I need to simply bring them up. Bring up the .66 interface using command IP link and set the interface up. Done. Then bring up the second interface. Okay, done. At this moment, if I run the command to check the IP address again, see, you see two new interfaces and they are both showing up. They have the corresponding IP addresses I just assigned to them. Now I have the interface ready. I'm able to construct the double tagged VLAN frames. Let's see whether we can reach out to the victim machine from the attacker machine. As I mentioned, I'm going to run 3 separate Wireshark sessions to capture from 3 perspectives. This top left one is for the attacker part. The top right one is for the victim part, but before the packet is sent out from the part. And the lower right one is from the victim machine perspective. It's after the packet is sent out from the part. So let me start capturing for all of them. As you can see now, I set the display filter to ICMP, so that's why you don't see anything yet. From the attacker machine, let me use the newly created VLAN 88 interface, ping the victim machine, run it. See, strange, right? In all the 3 Wireshark sessions, nothing's displayed. So let me stop the capturing. Let's try to understand what happened. Because in the attacker part, we don't have ICMP packet, which means the attacker Linux machine even didn't send out the ICMP packet. So the only possible cause for that is the Linux machine didn't know the MAC address for the destination machine. So why the attacker machine didn't know the MAC address? To understand that, we need to check the ARP packets instead of ICMP. So let me change the filtering to ARP in the first Wireshark. This attacker machine did ask around to see who has the IP address for the victim machine, right? So let me check a random one of them. See, even the ARP packet is showing double tags. That's expected because the interface we constructed in the way that it will carry the double tagging information. So we see VLAN 66 as the outer tag and then VLAN 88 as the inner tag. but it doesn't explain why we don't receive the ARP reply for this request. The Linux machine did ask around. Then let's move on to the second Wireshark. Let me change the filter to ARP. See, the victim part did receive the ARP request. And you know what? The victim machine did reply. Why it replied? Let's try to understand. So the received ARP request only has one VLAN tag. It is for VLAN 88. But in the left side, you can see the original packet does have the outer tag, which is VLAN 66. Why the difference if they are for the same packet? The reason is, so see the diagram, the attacker send out a double tagging frame, right? It will reach out to the switch with double tagging. Because this access part has native VLAN 66, so the switch will accept this packet even though it has VLAN tagging, but simply because the outer tag is 66, which equals to the native VLAN, so the switch will still accept it, right? So far so good. Then the switch need to forward the packet to the Pro 24 switch. And when it forward it, how it deal with the VLAN tag is depending on how we set the trunk port. And because the way we set the trunk port is it has native VLAN 66. It happens to be the same as the VLAN tag for our outer tag in our double tagging frame. The switch will forward the packet with the outer tag removed because the outer tag is the same as native VLAN, right? After the outer tag is removed, see what happened? All of a sudden, this frame becomes a legitimate VLAN 88 packet. When the Pro 24 switch receives the VLAN 88 packet, it doesn't have the VLAN tag 66 anymore. Our victim machine happens to be in VLAN 88. So that's why this packet will be forwarded to the victim machine, because the inner packet 88 equals to the native VLAN for this victim part. So that's how the magic happens. That's why this double tagging frame can even be forwarded by the switch and then reach the victim machine, right? That's what we see in this Wireshark session for this ARP request. Then see, this victim machine did reply, because from this victim machine perspective, this ARP request is a very legitimate request. There's no reason it doesn't reply, right? So it did reply, but let's check the reply. It doesn't have VLAN tag. Why? Because this victim part is set to access part, and for VLAN 88 is the native VLAN is untagged. So that's why the victim machine's reply doesn't have VLAN tag 88. But when the VLAN 88 packet is forwarded back to the Pro Max switch, it will still carry the VLAN 88 tag because the trunk part is set to allow all tagged VLAN, right? So the VLAN 88 tag will remain in the ARP reply when it reaches this Pro Max. But then because it's for VLAN 88 and our attacker machine is in VLAN 66, the VLAN 88 reply will not be forwarded to the attacker machine by the switch. That's also expected. So that's why in the right side Wireshark, you do see the ARP reply, but in the left side, you don't see it because the switch decides this packet is not for the attacker machine. So because the ARP failed, that's why the ping failed. But we are so close, right? As long as this attacker machine knows the MAC address, it should be able to send out the ICMP request, right? So now let's see how we can work around the ARP issue we just faced. Okay, so then go back to the attacker machine. The attacker machine doesn't know the MAC address for the victim machine. Let's try to make a universal valid MAC address for the victim machine. So the way to do that is to add a permanent MAC address, ARP record, to the system. I'm running the IP neighborhood command to add a MAC address, which is ORF. You may know ORF means broadcast address. I simply say, okay, if you want to reach out to this IP address, simply use this MAC address. And then this ARP entry is for the interface we just created for the double tagging purpose, right? In this way, I manage manually add a permanent ARP entry for the victim IP address. So let's see whether it works. Edit. So you see a error. It says the entry already exists. So let's see what's the existing ARP entry. Okay, yes, it does have one, and it says failed. Why is failed? Remember, we just tried the ping, right? And the system did try ARP, and it didn't receive reply. That's why here it says failed. And because of this ARP entry, we cannot add a manual one. Let me delete the existing entry first. Let me run the command IP neighborhood delete this ARP entry. Oh, I need to specify the device. Let me run the command again. Okay, it's deleted. Let's confirm. We don't have the entry anymore. Then let me rerun the command, add a permanent ARP entry. Okay, it's added. So we can confirm. Now we have a ARP entry. Let me restart the capturing. I still have the display filter for ICMP. Then from the attacker machine, let me ping the victim machine again. Okay, see all the 3 Wiresharks, they captured packet. However, from the attacker machine perspective, it doesn't receive the reply, so it's still hanging there. We will talk about that. Let me stop the ping first. Let's see what really happened. Let's start from the first Wireshark. See, the first packet was sent from the attacker Linux to the switch port, right? As we can see, it's double tagged and the outer tag is 66, inner tag is 88, and it is ICMP. This time, the Linux machine was able to directly send out the ICMP without ARP because we manually made up the ARP entry for the victim machine, right? So we are good. Move on to the right side Wireshark. Let's see when the switch port for the victim machine receive it, the same packet was not double tagged anymore because when the packet was forwarded from the first UniFi switch to the second one, because of the trunk port setting, the outer tag for VLAN 66 was removed. That's why when the packet reached the second switch, it only has tag 88. And then because the destination, the MAC address is RF, the packet will be forwarded to all the ports, including the victim port. And because the victim port has the native VLAN 88, so this packet was able to be forwarded to the victim port without any problem. And then move on to the third Wireshark. The victim machine did receive this ICMP request, and see, it didn't have the VLAN tag anymore because the victim part is a access part. So the VLAN 88 is untagged, right? So everything as expected. So then see, for the victim machine, it received the request. Of course, it will reply. And see, when it reply back, it has the correct source MAC address, the correct destination MAC address, and then it doesn't have VLAN tag again because the part is access part, right? Then move back to the second Wireshark. From the switch perspective, this reply also doesn't have VLAN tag because it's like what the victim machine sent out, right? So it didn't have VLAN tag. But when the packet was internally processed by the switch, the VLAN tag 88 will be added. So then the packet will be forwarded back to the first UniFi switch. But in the first Wireshark, you can see we don't have that ICMP reply anymore because that packet has the VLAN tag 88. Our switch port for the attacker is for VLAN 66. So that's why the VLAN 88 ICMP reply was not forwarded to the switch port for attacker. That's why from attacker, we still didn't receive the reply. But from all other side perspective, everything worked already. Let me pause here. Someone may ask, then what's the point if the attacker couldn't receive the reply? How the hacker can do anything if it cannot receive the reply, right? It may be a trouble for the attacker, but think about from the victim machine perspective. It did receive the packet. It did respond. For some protocol, if it need interaction, need acknowledge, maybe the attacker couldn't do any harm, but But for some protocols, they may not really require interaction acknowledgement, so the victim machine could do something following the request from the attacker without knowing that's malicious ask. Because this video is not a hacker tutorial, I will not proceed, but you already observe the harm is being done by the attacker. Even though for this particular example, attacker didn't receive the response, but the harm was already done. Then let's discuss for UniFi switches what we can do to prevent the double tagging attack for attackers to achieve VLAN hopping. From this Wikipedia article for double tagging, you can see how to mitigate the risk. So the first suggestion is do not put any host on VLAN 1. So for UniFi cases, it's the default network. This is not easy for UniFi switches, but it's doable, right? So basically what you need to do is when you define access part for a given switch part, do not set default network as the native VLAN. Okay, then the second suggestion is change the native VLAN on trunk part to an unused VLAN ID. In fact, this is the exact solution to the scenario we went through in this video. So let me explain it. In our testing scenario, the reason for attacker to be able to do VLAN hopping is because reason number one, the access part for the attacker part has native VLAN 66. Reason number two, the trunk part has native VLAN 66. To put it the other way, the trunk part's native VLAN is used by a access part, which is the root cause for the issue. So to mitigate it, apparently for this access part, we shouldn't use 66 because 66 is used in trunk part for native VLAN. And to translate to the wording of the Wikipedia article, what you need to do is to change the native VLAN on trunk part so that they use a unused VLAN ID. Okay, I hope it explains the mitigation step for this double tagging security risk. Okay, this is the end of the video. Thanks for watching.